Once again, welcome to the substation designing course. So this already we had last session on the how the course will be and what are the topics we are covering in this course. So this is the first class for us. So let's start with the preliminary engineering of the substation design. I mean that. So let's assume our project is a, 200 megawatt of wind power plant. So we are designing the substation for this 200 megawatt of wind power plant. Let me share you my screen, a whiteboard. Please confirm me whether you're able to see my screen or not. Are you able to see my screen, team? Yes, perfect. Okay, thanks for confirming. Yes. So you already familiar with the wind power plant. So wind power plant, all the wind missions will be located at some vicinity, and these are connecting to the substation where the voltage transformation is happening. I mean, the low voltage is stepping up to the high voltage, and we are connecting it to the grid. This is the grid. So this is a substation where we are focusing more and we are designing the substation. Why we need this substation? First of all, let's discuss for a while why I need this substation, and where to choose the location of the substation, and as well as the grid substation. So let's start from the wind point of view, team. So let's see. This is my area. Okay. We awarded a project of 200 megawatt of wind plant. 200 megawatt of wind plant. So this capacity will be given by our management. Addition to this capacity, we required the tariff for that project. Why the tariff? To check the reliability for our project, whether we are maintaining good reliability or is that much of reliability required for my project or not. I mean, to design my substation in a simple way, to design my substation in a less cost, or that the substation what I am designing, that should be a techno commercially viable one. So for to check that, we have to know the what is the tariff for that project. So the two things, one is the capacity and other one is the tariff. These are the two things we will get from the management, and also where the project is located. I mean, which location, whether it is located in the outskirts of Delhi or remote to in the northeastern, where we got this project, where the management noticed the potential of wind of 200 megawatt. So we need that data also, because we have to follow the guidelines of that utility when you are designing the substation. By how it is how what it means, that we will see in our next classes when I am talking about the layouts, when I am talking about the earthing designs. There at some places, at some instance, we have to comply to the standards of utility, not IEC and IEEE. Apart from that, we have to comply to the standards of the utility also. So we have to know where the project is located and who is the approval authority for this project. That is also second thing. So we will get the what is the capacity of the project and what is the tariff offering for that project, and the third one is the location of the project. If we get these three inputs from the management, as an electrical engineer, first we have to conclude the three things in the preliminary stage. What are those? First one is the voltage selection. We have to select the voltage and we have to select the substation and we have to select the grid substation. For selection of the voltage, we have to do some exercises and we will decide the what would be the voltage rating to be decided for megawatt scale. And the next is the substation design, a substation location choosing. So some technical factors and economical things we have to check when you are choosing the location of the substation. And the third is the grid substation selection, that we have to do some power system studies like load flow, short circuit, reactive power studies, everything, contingency analysis that we are doing in the ETAP software. So that is a one more thing we have to notice. We have to do that. So by this, we will come to know that, okay, to integrate, to export 200 megawatt of wind power to the grid, I required some X kV of voltage. And I have to place a substation here. And I am selecting the grid substation, this. So we will get some conclusion that will give you a broad view of your project. I mean, all these lines are connecting to the substation. The substation, the voltage is stepping from the X kV to the Y kV, and this Y kV is connected to some grid substation which is located in some other place. So you will get some broad idea of the project as a business point of view. Next, we are moving into the further stages of developing the project by doing the single line diagram, anything that we will discuss in the next classes. Fine. Now let's start with the voltage selection team. Let's start with the voltage selection. So let's share you my screen presentation. Give me a minute. So if you have any doubts, please comment in the chat box. I have already opened the chat box here, so I can easily view the message what you typed here. And at every 15 minutes, I will make a pause and I will ask you whether you have understood the concept still now or not. Don't worry, if you have any questions, don't hesitate to ask, please, Steve. Yes. So voltage selection. The transmission voltages for which the cost of the conductors, cost of the insulators, transformers, switchgear, and other terminal apparatus is minimum is called as a economical transmission voltage. What it's saying is, I will explain this with an example. Give me a little bit time to do this activity. Let's see this. This is my capital costing. This is my capital cost, and this is the transmission voltage. If my voltage is less, let's see. If I am talking about, if I am comparing the 33 kV to 220 kV and 400 kV, okay. Let's see. This is my 33 kV, where the transmission line voltage is this. Here for 33 kV, to establish the 33 kV system, and again the transmission lines, conductor, cost of insulators, everything, it is costlier. It is costlier. At what point? At some, it again depends upon the megawatt. It depends upon the megawatt. And if it comes down, if you are increasing the voltage, the capital cost is coming down up to at some point, and again it is getting increased. So we have to see this optimal point. I mean that, suppose the 200 megawatt of now let's go to the Excel. I will do an activity on this. Then you will understand what it is actually. Let's see, team. Do this activity. Let's see a 200 megawatt of power. Okay, 200 megawatt of power. If I am converting this into the amps, let's take the voltage levels. This is my 33 kV voltage. All the voltages are in kV. Please see, this is in the megawatt. hour in megawatts. Okay, and this is a 200 megawatt. 33 kV is the one voltage. Let's, for example, I'm taking, and 132 kV is the other one. 220 kV, 400 kV, and 765 kV. These are the voltage levels I am considering for transmission of 200 megawatt of power to the grid team. Please remember, 200 megawatt of power I am exporting with 33 kV, with 132 kV, with 220 kV, as well as 400 kV and 765 kV. If I am converting this power into the amps, then I am falling with the amperage of 1.732 root 3 into VI cos. You already know this, right? So into 0.95, I'm taking as a power factor for making it simple, into 1000. Just because if the megawatt I'm converting into the kilowatts. So this is the current thing. So if I am dragging this for all, so you can see the current that let me make it round off. So you can see that the current is if you are sending the 200 megawatt of power in 33 kV, so the ampere age is 3683 amps, and to send the 200 megawatt of power in 132 kV level, the amperage is 921. Okay, these are the amperes for us, amperes. Now, let's see. To send 3683 amps, you have to select the conductor. You have to select the conductor. So let's talk about the conductor just for 2 minutes. Again, we are having a separate class for selection of the conductor. But for time being, here I am showing you a brief view on the conductor team. Let's see. So where it is? Yeah, I think you're able to see the conductor sheet here. I will explain what is this all in the next classes. Of when I'm explaining each component, there I will come to let you know this this code, what everything. So let's see. These are the some conductors available with me. Here you can see the current carrying capacity. Up to for to carry in 33 kV, I required 3600 amps. But in this list of the conductors, ACSR, aluminum conductor steel reinforced conductor, as per IS 398 Indian standard. So the maximum current I can see is 998 amps, which is a Bursmis conductor on the size of 690 square mm. A size of 690 square mm, and the current carrying is 998 amps. Let's take 1000 amps for make it easy. Now, if I see the weight of this Bursmis, let's go top. Here you can see the weight of this conductor team. The weight of the conductor is a mass kg per kilometer. The Bursmis will having a weight of 2187 kg per kilometer. 2187 kg per kilometer. So if I want to, let me show the screen again. So if I want to, so what is the conductor exact amperage, which is 998 amps. So to carry 3683 amps, I have to lay nearly 4 conductors. 4 conductors. Okay, 4 conductors. So to carry each conductor, weight is 2187. Let's be 2200 kg. Let it be 2200 kg. So overall weight of the conductor is 2200 into 4, which is 8800 kg per kilometer. It seems that per kilometer, the conductor weight is 8000 kgs. But if you see the 33 kV structures, if you are familiar with the electrical system, the 33 kV structures are a wooden type of structures or with some RSJ pole, means RSJ pole of 192 into 192 or 230 into 230 size. Only a single pole, or sometimes you can see a double pole where the conductors are running on this with the height of this also only just 12 meters if you see the 33 kV network. But these structures, practically these structures are designed for the weight of 400 kg per kilometer. So now to carry 3683 amps, I have to select this conductor which is carrying 998 amps and its weight is 8800 amps. So these towers will not be suitable for my 33 kV one. So I have to go for a design of a big conductors where the towers using in for the 400 kV and 220 kV systems. For QuadMOS, it's obviously 400 kV, 765 kV towers I have to use for the 33 kV. Please remember, I am using 765 kV tower designs for the 33 kV voltage. See how the capital cost it is. How the capital cost it is. And similarly, okay, that is the one thing. Other thing is, let's see. Suppose, let's talk about the, this is about the practical scenarios, constraints of this. Now let's talk about the theory part of it, losses. So you already know the losses calculation is 3 into I square R. 3 into I square, which is this is square of this, into R. Let's take the resistance is 1 ohm. Obviously, the resistance will be changed for all because we are selecting different conductors. For time being, just I am taking to make it simple. So this is the number of kilowatts you are losing. Sorry, watts. Let's convert this into the kilowatts. Okay. And now let's take, this is the kilowatt. And if your generation, let's assume for time being, the generation is 24 hours and 365 days. Then this into 24 hours per day and 365 days in a year. I am calculating the losses per year. Now the tariff will come. What is the tariff for your project? My tariff for my project is 5 rupees, let's suppose, per kilowatt. Then what is the loss? Into 5 divided by, if I am converting into the millions, 1, 2, 3, 4, 5, 6. Right. So let's see the millions. So this is the loss. If I lay, if I am sending 200 megawatt of power in 33 kV, I am losing 1782 $1,782 million or million rupees. And if I am doing for 132 kV, this is the loss. For 400 kV, for 220 kV, 40 million I am losing. And 400 kV, 12 millions I am losing. And for 765 kV, 3 million, so I am losing. Again, what is the best in this? So I will pick 3.3 million. So I can go with the 765 kV. What about the capital cost? For if you're going for 765 kV, what is the transformer cost? What is the insulator cost? Again, the capital cost. So you are comparing the capital cost to the losses, and you are bringing the what would be the best economical choice for your system. Understood, team? So that is the point that was mentioned in the presentation. If you see the presentation, here I am talking about the transmission voltage for which the cost of the conductors, cost of the insulators, transformers, switchgear, and other terminal apparatus is minimum. The minimum in the sense, the cost as the cost here, not only the capital cost, your losses and what would be the returns, everything. So that we have to select as a, that is the economical transmission voltage. That is the economical transmission line voltage, transmission voltage for your system. Got it, team? Any doubts still now? Is it clear to all? Shall I move? Yes. So let's now see the advantages of high voltage transmission and what is the limitations of this. So now you can see the advantages of high voltage transmission: efficient transmission of large amount of power, saving in the conductor material, and you are improving the voltage regulation. What are the limitations? The losses and the capital cost, how to manage for economical project. Yes. Yes, it's a good question. As I said, now you are doing a rough calculation with respect in the Excel that if I am selecting a 33 kV network, suppose, let's see, let's go to the Excel again. Now let's see, if you ask me, then what I will generally do is, so for 33 kV network, okay, for 33 kV network, each line of the 33 kV to construct the bay and the substation, it's cost me 25 lakhs. So if I want two number of lines, so 2 into 25. Got? So 50 lakhs is my cost for 33 kV. In 132 kV level, each line outgoing one costs you 60 lakhs. So my cost is 1.2 crores. And for 220 kV, 80 lakhs, 1.6 crores, and 400 kV each dia. In 400 kV, we are having a concept of 1.5 breaker scheme. So 3 bays will become. So it's 3 crores or 2.5 crores. So it's cost you like 5 crore rupees there. And for 765 kV, it's cost you 7 crores for the 2 lines. So this is your capital cost, and this is your loss. Now let's compare this with 33 kV. Now what is the 33 kV? If I am going for 33 kV, what is the total cost? 1782 million plus 0.5 million. So total 1783 millions is my cost for my 33 kV. If I am going for 220 kV, I am investing 1.6 crores. So how much I am investing again? 1 crore. 1 crore I am investing more. But how much I am saving per year? See how much I am saving per year. 1782 minus 40. Am I right? Yes. So I am saving 1742. So point was nearly 774 crore rupees per year, just by adding 1 crore. See how much save it is. And similarly, if I am going for 765 kV, 7 crores is my investment. 7 crores is my investment. But how much I am saving from the 220 kV? 36 crores I am saving in 220 kV, suppose. So how much time it will take to get that 36 crores by additional having a 6 crores or 5 crores? It's taking me nearly 7 years to cover that. If your project is life is 10 years, then 765 kV is a good option for you. So like this we are doing, but don't see this is a wind project. In the wind project, there would be no continuous generation. So obviously there is no continuous generation. For the wind projects, the plant load factor means the average power of overall the year, it is only maximum 30%. So I can take only 30% here. Now if you check, then the 220 kV would be the best option. So this is the way how we are doing. So now here again one more point to be noted. So these already the state utilities and the CEA, Central Electrical Authorities, IEEE standards, all they have already done all these exercises, and they mentioned some guidelines that if your megawatt scale is this, then the economical voltage is this. I mean that, see, let's see this. This is the transformation capacity as per the CEA guidelines team. These are a recently amended one as per Central Electrical Authority guidelines of India. The voltage level, if you are having a 765 kV level, the maximum capacity is 9000 MVA. 400 kV, you can pump 2000 MVA. In 220 kV, 500 MVA. And 132 kV, maximum it is allowed is 250 MVA. So how they got this? By doing this, all these exercises, and they decided this would be the economical voltage for this megawatt. And in the American standard, they have mentioned this is the practice of in USA. This is the formula they have mentioned there. Now let's see. Let's do our calculation here. Let's take our power is 200 megawatt of power and assume the line length is suppose a 20 kilometers line. Okay, just implement here in place of 3P, three phase power, mention 200 into 1000. We have to mention the kilowatt as I mentioned below, into 1000 by 100 and 0.62 into 20. Okay, 0.6 into 20, it comes to nearly 1.2, right? So 1.2 plus 2000. So it's nearly to 2002, right? So square root of 2002, what is the square root of 2002? So it's nearly to 40 or some 30. Please check. Oh, wait a minute. We will check this. Square root of 2002. It's coming to 44.7. So this into 5.5. Let's see, this is a 246 kV. So I can go with some 245 kV. There's a highest system voltage. So 220 kV is the best option for me for that with respect to that formula. So like that, you can go. I'm not saying that you have to rely on this formula. Just you have to rely on this, on the utility guidelines or the practices what they are following in that area. Clear, team? Understood? Till now, is it clear? Yes. So that's about the voltage selection. So for our project, when this is the latest amendment one. So in 132 kV is nearly to 33 kV. So I am not selecting 132 kV. From this, you can select 132 kV for 200 megawatt. But I am not selecting 132 kV because some operations are will not come in 132 kV. I have to cover the higher voltages and also lower voltages. So I am considering a 33 220 kV for my application for our project. Because some of the concepts like auto reclosure, all this will not come in the 132 kV network. And the distance protection, those things are somewhat different there, which are similar to the 33 kV. So for our project, we are selecting 220 kV is the best economical voltage for our project to export 200 megawatt of wind power to the grid. Clear, team? Am I clear? So this is the grid, this is the substation, and this is the wind farm. Then I selected to carry 200 megawatt, the 220 kV is the best option. Fine, this is good. But will the wind farms generating the power in 220 kV? No. All the wind farms across the global, most of the wind farms, they are generating the power in 33 kV voltage. The output of the wind farm is 33 kV, team. See, I'm just giving you just an idea of the wind farm. This is the wind farm fan, and we are having a top one, and this is the hub, and these are the fans, and this is the how it looks. This is the tower, this is the hub, this is the fan blades which rotates, and this shaft is connected to some generator. This generator is generating 2 megawatt of power. Each wind turbine will generate 2 megawatt of power in 690 volts. In 690 volts. So this 690 volts is stepping to 33 kV at the top. This is the transformer. The rating of transformer is 2.35 MVA, and it is a dry type transformer which is stepping up the 690 volts to 33 kV, and this 33 kV comes to bottom through a cable, and we are having some SF6 circuit breaker here, and this cable is 3-core 185 square mm cable will come as a out. So the whole design, maintenance, testing and commissioning, erection, everything of this wind farm will be in the scope of OEM only, manufacturer, like Siemens Gamesa or Suzlon or maybe Veritas. So these are the main players in this wind fans. So they built everything, and they will give a 33 kV, 33 core 185 square mm cable as a out. So from this cable, our design works will start. So each turbine is generating 2 megawatt in 33 kV voltage. So for our 200 megawatt, we have to install 100 numbers of wind farms. So all these wind fans are connected and to be pooled at one location, where the 33 kV has to step up to the 220 kV, and that 220 kV you are exporting to the grid. So where the stepping up the process is going on, that I am calling it as a step up substation, where the transmission of transformation of the voltage is happening, which is stepping up the power from the low voltage to the high voltage. So I am calling that substation as a step up substation. If you are seeing from the grid, there the 220 kV, the grid power, the 220 kV is stepping down to the 33 kV, and you can feed to the loads. So that it is called as a step down substation. See, the design of the substation, it could be whatever substation is same. When you are, suppose, if you remove all the fans, if you are placing the motors at the 33 kV, then it is a step down substation. It's a distribution substation. If you are adding some solar or power generation as a source, and you are exporting the grid to the power to the grid, then it's a step up substation. That's it. So it's totally depends upon the what is the action of that. So that is the classification of substations. Based on, we have to classify the substation based on the two things. One is the service requirements, other one is on the constructional features. As I said before, Based on the service requirements, the transformer substation, switching substation, power factor correction substation, converting substation, or industrial substations. These are the substations related to the service requirement. And come to the external construction features, outdoor substation, indoor substation like GIS, underground substation, and pole mounted substations. So these are the some constructional based on the constructional features. But at every, these are the what that substation doing. If the substation is stepping up, stepping down the power, then I will call it as a transformer substation. If that substation is only connecting the lines and leaving the lines, then I will call it as a switching substation. If the lines are coming from 4 kilometers, and if I want to do some reactive power compensation there by adding some shunt reactors and capacitor banks, then I will call it as a power correction substation, power factor correction substation. And if I want to convert the HVAC to the DC, AC power to the DC, and I want to transmit the power in DC lines, HVDC, I will call it as a converting substation. If I am using the substation for my industrial power application, I will call it as an industrial substation. So what is the service? But on all these substations, the design is common because we are talking about the substation.